Hello everybody, welcome to the 8th section of Unit 1 Tools of Geometry, three-dimensional figures. This can be found on page 76 through 83 in your textbook, approaching page 100, which is already insane considering how little we've covered in the whole scheme of geometry and how much more fun we have to go. So let's look at those two objectives. Identify and determine different components of three-dimensional figures, which we'll look at in the first few slides through a flow chart and some practice problems. And then we're going to evaluate or solve for missing measurements in three-dimensional figures. That's a very key idea of this whole chapter, focusing on if I give you a three-dimensional figure with specific measurements, does that mean I need to evaluate for something, or am I solving for something, then evaluating? So we'll get into all that detail, actually in a separate video that is also with this section. You'll see that link in the bottom right-hand corner later in this video. All right, let's get started. So, first thing to look at is the two distinctions between a polyhedron and a non-polyhedron. A polyhedron, as you'll see in a definition pop up on your screen in a moment, let's see, there we go, is a solid with polygonal faces and bases. The actual root of the word simplifies to many-sided solid, very important. But if we look at that, that's basically indicating that a polygon, starting with a three-sided shape, which is a triangle, anytime it has a triangle or more sides combined, it is going to be a polyhedron, which we'll see three different types of those in just a moment. If it doesn't have those polygonal sides or has no faces or edges, that's what we call a non-polyhedron. And if we see the picture of that, we understand that a cylinder, cone, sphere, and a new term for you called a torus, which is the same as a donut, or the same as taking a piece of paper, rolling it up, so it's this giant cylinder, and then connecting it into a ring. So a very common shape, but definitely something new to our vocabulary. All of those are examples of a non-polyhedron, because they're all solid, obviously, but there's no faces or edges where they connect, which you'll see what I mean by edges in the next slide. So let's keep looking at these polyhedrons. First one to look at is what we call a prism. This is like a very fancy way to say a cube, right? A cube is a type of prism. But let's take a look at what makes it a prism. Prism has two important key ideas. Two parallel bases. So if we look at all three examples, there is two of the same thing. Two triangles in the first one. Two rhombi, if it is a rhombus, I believe it is. Or a square or a rectangle. All could be all of each of those three. Or lastly, a pentagon, right? That pentagon, top and bottom. They're all connected by these faces, which if you're looking close enough, you might be able to tell that all the faces are the same shape, which we'll kind of get into that further in class down the road. But again, a prism has two of the same bases, and that gives it its name. So that first one is a triangular prism, second one is a cube or rectangular prism, and the third one is a pentagonal prism. Now how is it different from our next one, which is a pyramid? And maybe you can already tell just by looking at a square prism versus a triangular prism versus a triangular pyramid. Well, the big distinction, it has one base and the faces are connected at one vertex. And we know that it's very common in Egypt. We talk about those pyramids that are there, but that's just one type of pyramid. Those are all square pyramids. Very important distinction that there are very other types of pyramids, not just a square pyramid. Most common, but not the only one. And let's look at that last category called platonic solids. And each of those platonic solids look super different, but how they're all under this category, this big umbrella, is all of their faces are congruent. So that first one is a triangular pyramid because it has four of the same triangles, and that's the only shape. The next one is a cube. 6 sides, all of those faces are the same. The next one's called an octahedron. All of those 8 different shapes are all triangles, all of which are congruent. And you can continue to go down the line to the dodecahedron and isohedron. Now, all of those edges are also the same. So every length from each vertex is identical, which we can't say that's the same for the prism. Because if you look at the triangular prism, the pieces, the edges that make the triangle are much smaller than the edges that connect the two bases, the long pieces to the edges of those triangles. So let's take a look more about that vocabulary, what I keep saying, faces, edges. Let's see what those actually are. So in a three-dimensional solid, there's three main vocabulary terms. Technically a fourth, we'll get into that, which that one's called a base. But the three we're focused on now are an edge, face, and a vertex or corner. The edges are those little line segments that are connecting those faces. So every single time there is a square side, as you can look in this cube, on the tan one, every one of those four sides are all considered edges that are connecting to each other, which we'll get to what that connecting point is called. But there's many, many edges in this collection of this cube, which we'll explore that in some example problems, how many there are in a pentagonal prism, how many there are in an octahedron. We'll go over how to be able to identify all of their edges. Then we're going to look at the faces. Those faces are that, in this case, are all squares, but those faces are all connected by those edges, right? So if we're rolling a dice, or one die, we recognize there's 6 faces on that die. We know that. But if we looked at a different type of shape, a different type of 3D shape, it might have obviously more or less faces. And then lastly is that corner, which is more commonly called a vertex, or plural vertice, which we'll talk about that, or vertices. Now, each of those corners connect the edges and the faces together. So if you look at a cube, every corner is connecting 3 edges, right? And technically 3 faces as well. So if you're looking at this initial corner in the bottom right, or the top right here, you can see that it's this corner connecting the yellow and tan. This corner is connecting also the orange and yellow, and then also the orange and tan all in one point. So all 3 faces and edges are connected at one vertices. Now, if you look at our practice problem here to the right, it says determine the number of faces, edges, and vertices / corners of the shape below. We're looking at this square pyramid of JKLMN, right? You name it by all of its vertices. Don't worry about the L, H, and S. Those are talking about sides, height, and slant height, things we don't need at the moment. That's only for when we're doing measurements. But there's a table there to figure out. Go ahead and pause the video, see if you can determine each of those 3 different things, and go hit play. You'll see the table is posted for you. Alright, so there's the results for your table. You can see that there are 8 edges. There's 4 around the square at the bottom, and then 4 for each of those lines that connect each triangle at the top. Faces, yes, so that makes 8, I apologize. Faces, we've got the base at the bottom, which is 1, and each of the 4 triangles, which makes 5. And vertices and corners, which also are 5, because there's 4 in the square at the bottom, and 1 connecting at the top. And there are some patterns to be found about other types of pyramids based on looking at their tables, which we'll explore in class. Alright, take a minute, take a breather. We'll come right back. We're going to look at our second video, which is what we do to evaluate or to solve when we're given these measurements. Thanks, everybody.